Welcome to the 26th lecture video for Physics 4a. Having introduced the waves in the last lecture, in this set of lecture videos, we look at a few wave phenomena, in particular focusing on a couple interesting examples of wave superposition. As we start, the first thing to cover is what happens in wave interference, or more precisely what doesn't happen. Despite the word interference, when two waves overlap, they don't affect each other. This is captured in the superposition principle, which says that when two waves overlap, their overall result is a simple addition of each wave function. Exactly what happens when there is no interaction term between the two overlapping waves. Having emphasized this superposition principle, we apply it to the standing wave, a result of an interference between two waves propagating in opposite directions. You can see that even though the superposition principle sounds very simple, it results in complex and interesting overall behaviors. Another example of wave superposition is beat, whose mathematical treatment is given in this lecture. And I hope you see the similarities between the mathematics involving the standing wave and the beat phenomenon. Lastly, we have a couple lecture clips that cover topics that fall somewhat outside of the main topics we cover in this class. Treatment of standing waves with a complex exponential is certainly outside the standard curriculum for Physics 4a. But for those of you who follow the complex exponential material relating to the simple harmonic oscillators, I think this would be an interesting follow-up practice. While the Doppler effect and the shock wave are within the typical curriculum for Physics 4a, outside of one homework question, we don't give them much emphasis, mostly in the interest of time. This is it for waves. As before, we have a set of timed assessments next week for you to practice your understanding of oscillations and waves. And we are almost ready to wrap up this first semester of calculus-based physics. So maybe I should start out with a discussion of wave interference as a sort of reminder of what we have been talking about. So when I say wave interference, do you feel like it's something that you know something about, like it doesn't sound new? What does it mean for waves to interfere? Like, what does this mean? Does that mean like, does that mean, you know, I have some wave somewhere and like, does it mean some kind of an interaction between waves? As in, you know, if I set up a wave and I get wave interference when there's like two different waves on the same medium. So I could like send out one and then send out another. As they come together, they interfere. Yeah, it's I mean, the way it's stated right now, it's a little bit vague. It could mean that. But so this is, I guess, maybe more important question. When two waves interfere, do they interact? Does one wave affect the other wave? I want you to come back to this simulation, especially for those of you who are nodding. Because if you're nodding, you probably weren't paying attention last week and the week before. So this is what you saw last time with the simulation. It's a lot easier to demonstrate with the simulation, which is why I do this. When you see two waves, let me do it with a loose end. Slow motion, no damping, fairly small pulse width. When you have two waves here, one, it's gonna go, bounce, and come back. As they interfere, as they overlap, as they interfere, they do not affect each other. So I guess here it's hard to see. Watch these two waves interacting. As they come together, so the upright pulse, was that affected by this other pulse that it met on the way? No, right?
So let me just go back to the beginning and do the fixed end so that I can do this without having gone through this twice. So when the pulse 1 and pulse 2 meet each other, do they affect each other? They don't. The pulse 2 continues on as though pulse 1 was never there. Pulse 1 continues on as though it never met pulse 2. Now, we do have to handle at the moment they are meeting. At the moment they are meeting. This is the moment where we have to handle it somehow. And when we talk about wave interference, we are really talking about moments like this. This is what we are calling wave interference. So when two waves are interfering, in what sense are they interfering? Because we just went over, I re-emphasized that one wave does not actually affect the other wave. They pass through each other. Two waves interacting with each other is very different from other kinds of interaction you have seen. Like if you have two balls interacting, then as they overlap with each other, they don't really overlap. They bounce, they affect each other. But waves don't do that. Waves can actually overlap. And that's one of the conditions you need for interference. For two waves to interfere, they have to occupy the same time and space. They have to overlap. So as they're overlapping, what do? Like, is there any principle that you learned that gives you a rule on how to handle two waves overlapping? Steven? Yeah, superposition principle. So when we talk about wave interference, you can replace this with the idea of superposition principle. And I just want you to remember that we give it a fancy name because the thing that you do for superposition principle is such a simple thing. So what you have with wave interference is that you have two waves. Let me call one wave F1. That's a function of position and time. So it's a function of position and time. And you have another wave, like those two pulses there, F2. That's also a function of position and time. And some of these positions and some of these times will overlap. So that there will be time where two waves are overlapping on top of each other. And with the superposition principle, what we are saying is that as these two waves overlap, as they overlap, this is the combined, the net result of these two waves. The net result is simply a sum of these two. They add, they don't do anything else. They just add, and that's it. And I guess this class is a little bit too early to spend a lot of time on this, but for those of you who will be taking Math 3 in the in the near future, and you will be doing upper division level work in engineering and science, this is related to a property called linearity. This idea comes up a lot in both physics and mathematics. This is the linear property that you will see in linear algebra in Math 3. And linearity does mean something physically. Physically, when two physical quantities exhibit linearity, physically what that means is that these two physical things don't interact with each other. So, for example, the interaction between these two, they are not linear. It's highly nonlinear. So as they start to overlap, they do affect each other. They bounce and affect each other's path. So with waves, because they don't interact with each other, you can simply add them. You don't have to have any other interaction terms that describes how one affects the other thing. So anyways, I'll just leave it there because we don't have the language to describe it better than that. So So when we talk about wave interference, really this is all that we are applying. And because this sounds simple, once you understand it, it should sound simple. This is not some complicated principle. I want you to point out some interesting examples that are result of wave interference. And in fact, you have seen one of them already. Do you remember one of the examples of wave interference that you have already seen? That we worked out on Tuesday, actually. We did it before the end of the lecture. And you had a whole lab on in Asia. Yeah, standing waves. So standing waves was a result of an interference between two waves. Let me just, I won't write down the whole thing. You can look in your notes and I'll eventually post last Tuesday's video. But as an example, with the standing waves, so the total wave was a sum of two waves propagating in opposite directions. So one wave might be moving to the right. I could describe that as some amplitude times cosine of kx minus omega t. And when this overlaps or interferes with a wave that's traveling to the left, that would be a times cosine of kx plus omega t. It's this sign here, minus or plus, that tells you that this wave is moving to the right, this wave is moving to the left. That as they overlap, they create a pattern that results in nodes and antinodes. And you have seen them in the demonstration, and the lab you did on Tuesday was based on this. Yeah? But do you know any applications of standing waves? Like, I did tell you like 2 weeks ago that waves are the most important thing we do in this class, but I don't think I ever really demonstrated it. Waves are so important. Where do you see waves that are, I don't know, relevant, practical?
Communications jamming.
Okay. What if I never become a spy and I don't want to jam anyone else's communication? So there could be an example of interference, but it's more of just overwhelming someone else's signal. I want examples of standing waves, actually. Standing waves are actually, there are a lot of examples. In fact, there are examples of standing waves in quantum mechanics that you might eventually see. But I want you to think of more mundane example if you have seen standing waves anywhere. There are many examples. Anybody here do music? Guitar, piano, wind instrument. Nobody here does music? Okay, some of you. Music is impossible without standing waves. So I keep bringing this out. This is the first time I'm actually having time to bring this out. So this is a guitar. The principle on which guitar works is a standing wave. As in, I have this string, and when I pluck it, when I pluck this string, it emits a particular pitch, particular tone. And why that's associated with this vibrating at a particular frequency. And so, why does it vibrate at that particular frequency and not some other frequency? It's because when I pluck this string, they are out of tune. The most natural way it would vibrate is a frequency that forms a standing wave on this wave. And similar principle works for almost any other musical instrument. Except for your maybe vocal cord. But even then, the kind of sound that you can more easily produce is affected by the shape of your whatever. So I will actually use this example a little bit more later. But so music is one of the biggest application of standing waves and waves at this stage. That's why there's a whole chapter on it in your textbook. Sound waves, and it's a good sort of topical area to develop your intuition for waves. But I just want to tell you right from the beginning that the application for waves is much greater than just this narrow area of music that apparently very few of you have interest in anyway. What I want to spend the remaining 20 minutes or so right now to talk about is standing wave, definitely. And I think we might have time to talk about something called the beat. So I'll try to get through standing wave as soon as possible. So standing wave is sort of what it sounds like, wave that's a standing. So I want you to take that as a contrast from what we've been talking about so far, traveling wave. So when you look at this wave, it's obviously traveling from left to right, right? So that's traveling wave. So I want to try to get this wave to be standing, not traveling anywhere. So the obvious thing to do might be this, put an end here. So let's put a fixed end there. Oops, let me restart. So that might be something you do. But when you look at this over some period of time, you see that the kind of motion you get, it's really complicated motion. So, I mean, it's clearly not traveling anywhere, but I wouldn't also call this really standing. This is a very chaotic kind of motion that, neither traveling nor standing, right? So to get something that we call standing wave, you have to meet I didn't expect that. You have to meet a very particular condition to get something that we are going to call standing wave. So this is where I want to remind you of what we called wave superposition last time. What happens, wave superposition, that's the question of what happens when two waves overlap. As in, you have a wave F1 and so F1, that's a function of position and time, that's overlaps with F2, the function of same position and same time. So when these two waves overlap, what is the overall result of those two overlapping waves? We talked about this last time, right? Kinda. Do you remember? They simply add. That's the rule. It's a sort of a kind of amazing coincidence that that simple rule describes what actually happens. So we call that superposition principle. Superposition principle is that the overlapping, the combined wave F is simply the simple sum of the two components of that overlapping waves. So the reason I'm mentioning it is I want to think of the standing wave that we are going to develop as a sum of two waves. So here's one way actually you can kind of imagine it here. Let me go back to pulse mode here. Then what I can describe standing wave as is as a sum of a periodic wave that's traveling from left to right as represented by this pulse, and a periodic wave that's traveling from right to left as represented by this pulse that's traveling from right to left. Because of this reflecting boundary, that's what you are going to have. When you put in this oscillating wave from left, then over time, it'll reflect from this end. And right now here, it's difficult to see. But the in-between motion that you see here is a result of two waves that are adding together. One wave that's traveling from left to right, another wave that's traveling from right to left. Now with the standing wave, we need one more thing. We need to fix the frequency at a very particular value. So when we are talking about traveling wave, this frequency could be anything. There was no real condition on it. But here, when I set this frequency to be anything, you don't get standing wave. The shape you saw, that's not what we describe as a standing wave. So let me make a quick measurement to get the correct value of frequency. This is the quick measurement I'm going to make. Here's a special amount of time that will help me set the correct value of frequency. So let me have my timer here. Let it run. So when I start running simulation, the timer will run as well. So I'm going to see how long it takes for a pulse to travel from here to the end here. So that amount of time, okay, so I need to do it frame by frame. All right, something like, okay, 1.18 seconds. All right, so let's call that the period. I need a frequency that's associated with that 1.18 second. So 1 over 1.18 seconds. I could have just 0.85 hertz. So I feel like that's a special frequency. So let me set my frequency at that value, and let's see what happens. 0.85 hertz. And actually, I'm going to reduce the amplitude way down for the demonstration that I'm going to do now. Let me set this back to normal, get rid of the timer. Let's see what happens. So this is what you are going to begin to see happen. So I set the frequency at a very particular amount of time so that the period of my oscillation is the exact amount of time it takes for the wave to travel from here to here, which means, let me write this down. So let's say I describe this as the distance L. And if I set my period to be equal to the amount of time needed to travel this distance, that'll be L divided by wave speed, right? So, or in other words, the distance L here is equal to period times the velocity, or rewriting period as frequency, yeah, that happens over time. So I don't get rid. So period as frequency 1 over f. So L would be V times or V over frequency. And looking at this, looking at this expression that we are working with before, that L there is equal to the wavelength. So here, this distance L, when this distance L is equal to the wavelength lambda, then that's when you get this pattern that we call standing wave. And when you look at this wave carefully, you can intuitively see why we call this a standing wave. This wave has the points that don't really move. So some of the points don't move for a good reason. The point at the very end, it doesn't, so once again, that sort of change in the amplitude over time, ignore that for now, that's an artifact in the simulation. But the point at the end, that point doesn't move for a very good reason, that's a fixed point. I clamped it down, I made it so that it cannot move, right? The fact that point here doesn't move all that much is actually more perplexing, because it looks like that's the point where I'm shaking, right? So what I mean that the point doesn't move. It doesn't move compared to the rest of the wave, because look at how much oscillation happens here. Compared to that, amount of oscillation that happens is practically 0. So that's what I mean, this point doesn't move. And here's the weirdest thing. Is there any good reason why this point should not be moving? So that's a description. Well, actually, we want to be careful with the word amplitude. Amplitude refers to the entire wave. So I would not talk about amplitude over this single point. Think what you mean by amplitude is the displacement. And when you say displacement is very small, you're simply rewording what I already said, that this point does not move. I'm asking you, is there a reason why the displacement should be small here? So it's going to be the result of the superposition. And I'll show this to you in math. But when you just, aside from superposition that we'll look at soon, there's nothing holding this bead here. So there's no physical reason like these two endpoints that this point should be a non-moving point. But this is a feature you see in standing wave. There will be points along the medium where the displacement is 0. And the only thing that's causing the displacement here to be 0 is the wave superposition, or what we call wave interference. It's the addition of wave that's traveling from left to right, and the addition of wave that's traveling from right to left. They add in such a way that at this point, they always add in a way that they cancel out. And how that happens will depend on the frequency. So we use the frequency 0.85 hertz. You can actually go a little bit lower and get another standing wave. So let me do that. I can actually go at half this frequency and we'll get a standing wave. So let me go to 0.42. So 0.42, and then I'll reset. And you will see a standing wave building up over time. By the way, one way to intuitively describe this is as an energy building here. This thing shaking, it's trying to do work, and somehow the timing works out so that each time it shakes, it's doing positive work. And it's putting energy into this string system. And so if this reminds you of the resonance that we talked about in oscillation, it should. This is an example of resonance. This wave system has a natural oscillation frequency. This would be the lowest of those natural oscillation frequency. And when you shake it at that natural oscillation frequency, you can build up a very large amplitude using very small amplitude of driving oscillation. So this is an example of the, this is what we also call fundamental harmonic. It's the lowest frequency oscillation. You have two fixed points at the end. Those have to be fixed points. And you saw what happens when we double this frequency, right? Let me give you the triple this frequency and let's see what happens. So if I triple the frequency, let's see. So 0.42, triple 1.26. And I'm just going to add the 1 because there's this little rounding thing that I have to worry about. So I'll set this at 1.26. I'm sorry, 1.27. So 1.26 is the exact triple of what was there, but there's a little rounding thing I have to worry about, so I'll just add 1. All right, so restart, and let's see what happens. So this is what you see. You see these stationary points showing up as once enough time passed for this standing wave pattern to build up. Okay? So this is probably a good picture for me to use to introduce a couple terms that we use to describe features in a standing wave. So these points that I have marked here, these points, we call them nodes. So these are called nodes. Definition of node is that it's a point that doesn't move in a standing wave. Or this is the standing part of the standing wave. And as long as I'm talking about nodes, let me talk about antinodes. So what we call antinodes in a standing wave are these points. Sort of the place right in between the nodes. All these points are what we call antinode. It's sort of what it sounds like, the opposite of node. So if the node is the point on the standing wave that doesn't move, antinode is the point on the standing wave that moves the most. Good? Okay, so let's see how this kind of shape that you see happens. So, so this is the mathematical derivation of how this standing wave happens. So, so let me describe the mathematical form of these functions f1 and f2. And what I will show is that the resulting mathematical form naturally can be described as what you are seeing here. So I'll get an expression for f, and that'll look exactly like what you are seeing on the screen. So f1 is going to be traveling periodic wave, what we described here. This will be the form of f1. So one of the two waves that add is a wave that's traveling to the right. That has some angular frequency omega. So given some wave speed, it's going to have some wave number that's associated with its actual wavelength. So that's F1. That's equal to some amplitude times sine of kx minus omega t. And this is the wave that I'm generating from this oscillation source. There must be a second source of wave that I'm going to be adding to this. Where is the second source of wave? I mean, if I have a single source of wave, then it'll be like a traveling wave that should just move off to the infinity. There's one more source of wave. Where's the second source? On this physical demonstration.
That's holding the other end.
Yeah, so this is the place where it reflects. One way to describe reflection is that when the wave reaches this point, it becomes a wave that's traveling from right to left. That has otherwise the same properties as the original wave. So let me write down an expression for that second wave. It's a wave that's, I need to reserve a little more space for myself. So F1 is a sine of kx minus omega t. And the second wave that's coming from the point where I'm holding is equal to a times, all of the properties will be the same amplitude. And I can even keep the same sign. So sine of k, I can keep the same wavelength because the frequency of oscillation is the same. So it'll be same kx. And this is the part it's going to be different. Instead of being minus omega t, it's going to be plus omega t, which will be, so this describes a wave that's traveling from right to left. Do you see that? Yes. Yeah. One way to see is that as you increase time t, to keep this quantity kx plus omega t constant, so you're trying to track the wave at the same point in its cycle. As you increase t, x has to decrease. That's why this describes a wave that's moving from right to left. Okay? So, all right, so let's write down what f is using wave superposition. F is equal to this plus this. So I guess I can factor out a times sine of kx minus omega t plus sine of kx plus omega t. All right, so you look at this expression and think this does represent what I see on the screen there. Yes? For most people, that won't be the case. Like, it's very unclear how this relates to the shape that you're seeing there. So let me go through a little bit of trigonometry to rewrite this in a way that you can relate it more easily to that shape that you are seeing. So this is where you need the trig identities that I've mentioned several times this semester. This is the most useful trig identity that I know that a lot of people forget. It's the angle addition formulas. So the one I'm going to use here is the sine angle addition formula. Sine of alpha plus minus beta is equal to sine of alpha cosine of beta plus minus sine of beta cosine of alpha. But let me write down the other one too in case you need it in the future. Cosine of alpha minus plus beta, let me write down the usual way. Alpha plus minus beta is equal to cosine of alpha cosine of beta minus plus sine of alpha sine of beta. This sounds familiar? If you don't have it memorized, you have seen it before at least? Yes? Yeah, so let me use the first trig identity to rewrite this, because I can clearly see that this is my alpha, this is my beta. So I can use that to rewrite it, see what happens. So the combined function is equal to a times, let me rewrite this, sine of kx times cosine of omega t minus sine of omega t times cosine of kx. All right, that seems complicated. Let me write down the second one. Plus sine of kx times cosine of omega t plus sine of omega t times cosine of kx. And this is where you see something magical happen. You see these two complicated terms canceling each other out. And when you look at the remaining term, they are exactly same as each other. So this plus that is just double the one of them. So when you simplify all of this, this is what you end up with. That this function f here is equal to 2 times a and this. Sine of kx times cosine of omega t. Now, does this represent the shape that you are seeing? Yes? Yeah, I mean, look at it. So imagine fixing the time. Freeze the time at any time. So that at any time, that's not where cosine of omega t is not equal to 0. Then what you see is that you get the remaining term gives you something that's sinusoidal in shape, right? And it's always in such a way that the beginning point is at 0. And wherever value of x is, so the sine of kx is, or kx is equal to some multiple of pi, the sine of kx will be 0. So this is where kx is equal to pi, pi, 2 pi, 3 pi. Yeah? And now imagine stepping forward in time. As you step forward in time, whenever time value t is so that cosine of omega t is 0, then your displacement everywhere throughout the wave is at 0. And as you step forward further in time, so the cosine of omega t is not 0, but like -1, then you get the flipped over version. So this function almost exactly describes what you are seeing here as a function of time. And this is how you derive the mathematical form of the standing wave. It's nothing more than addition of the two traveling wave. The one that's traveling to the right and one that's traveling to the left. That has the same amplitude. And you go through a little bit of trigonometry, and this is what you end up with. It's a very simple simplification, but not one that's necessarily easy to get, at least until the first time you see it. One more example of wave interference that I want you to have time to go over is one that you see most often with the music. But once again, you will see future applications on this, I guess I keep saying it, quantum mechanics again. So this second example that I want you to see as an example of wave interference and why this simple mathematical procedure leads to something interesting that you wouldn't have guessed. The second example is something called beat. So I mean, I won't ask like what beat means to you, because like heartbeat, or it kind of has nothing. The way we are going to use the word beat has nothing to do with those. So beat is it's an interference phenomenon. Interference phenomenon that happens with two sources of wave, or two sources of oscillation even. Two oscillations that's happening at two different frequencies, with two oscillations at different frequency. Let me start out with a demo because I think it's different frequencies. Let me start out with a demo because it's easier for you to first have seen the phenomenon and then try to explain it mathematically how that happens. So let's see. Anybody here know the frequency to musical scale by heart? No one here does? Okay, never mind. Let me not do musical scale because I have to look it up and I don't want to. This is a software that can be used to actually record the sound. You can see that it's recording me right now as I'm talking. Yeah. So
can say that.
All right, and I can use this to generate sine tones, like what you are dealing with in the lab. So I can use this to generate, I don't know. You guys are dealing with the 500 hertz tones in the lab, right? So I can generate a 500 hertz tone. Something like that. Fairly annoying, loud, yeah. It kind of has to be loud. All right, and so, on this software, because 500 hertz means in 1 second, it's oscillating 500 times. That's why you don't see it individually. But I can actually zoom into a fine enough scale that I can actually see the sine wave or cosine wave or whatever. All right, so that's a 500 hertz sine wave. Now, let's see, okay. Let me get a new track. What if I generated, I don't know, if I generated 550 hertz tone, do you think you can tell the difference between 550 hertz and 500 hertz? All right, that was 550. Does it sound different? That sounds different enough. Like most of you, like if you close your eyes and then I play one of the two, if you just recently heard it, then you could tell one is 550, one is 500. All right. What do you think this will sound like if you hear them together? Let's give it, I haven't actually tried it. Let's try it. Wait, where do I? Okay. Does it sound like either of them individually? It doesn't, right? And in fact, if you're into music theory, this is where the whole theory of, harmonious and dissonant combinations are based on. I won't get into that because I don't know much about music theory. So what I want to look at is, here it just sounds somehow different to you. Your ear can tell that it's not just the 500 hertz, it's not just 550 hertz, but like what it is you can't quite tell. I think it'll be easier for you to tell what's going on if we generate a frequency that's much closer to 500 hertz than 550 was. So let me generate something that, I don't know, let me try 505. I haven't tried that before. Okay, so this is 505, and this is 500. Can you tell the difference? Yeah, I mean, most of you, if you think you could tell the difference, try closing your eyes, and I'm going to randomly pick between one or the other. I'll randomly pick one. Do you think it was 505 or 500? Right, you can tell, right? It was 505. Yeah, if you could tell it, you might have perfect pitch, but whatever. Now, what do you think it'll sound like if you hear them together? Let's try it. It sounds nothing like those two individually. And you can visualize it better. So, if I just zoom in like this, like from these shapes, it's not clear exactly why that would be happening. So let me use this particular feature of this Audacity software. It can do what's called mix and render the tracks. As in, this is like having two different sources of sound. One at 500 hertz, one at 505 hertz. And with the mix and render, what it'll do is it'll combine the result of interference of those two waves, do this superposition principle thing, and give me the combined result. So mix and render to a new track. And this is the result that you see. And once you see this wave shape, then it should make a little more sense why you are hearing what you are hearing. Like, can you guess like why you are hearing what you are hearing? Sorry. Let me zoom in a little bit. Like why are you hearing what you are hearing? No, I mean, I want you to just look at what does this waveform represent? Like if you simply just saw this waveform, like what would you think this should sound like to you? like a beeps. It gets louder, quieter at a regular interval, right? And that is what you're hearing. When you hear it, it's loud, like loud and quiet at a very fast 5 hertz interval, actually. Yeah? So that's what you're hearing. And so this is what we call bit. It's the result of interference between two waves of a slightly different frequency. And what I want to show is mathematically, analytically, that you get a shape that looks like this, like a wave that's an envelope, that's inside an envelope, so that its amplitude of oscillation is changing at some regular rate. Okay? So let me go through the math. This is one of those things that once you see it, I hope it makes sense to you, and you can maybe even do it for yourself later. But the first time you see it, it's kind of hard to figure out all the right steps because it involves some less motivated steps. So let me work through that. So for the bit, you need to have 2 sources of oscillation. So this time I'm only going to deal with the function of time. It makes sense because when I hear sound, I only care about one location of my ear. So I don't really have to think about the whole wave as a function of space. I can just reduce it down to, I only care about oscillation in one location. So I have 2 functions, f1 as a function of time, f2 as a function of time. And both of these, I can describe them as some periodic oscillation. So they have some amplitude times, let's call this cosine of omega 1 t. So this is the angular frequency of this oscillation. In the example we are using, omega 1 would be 2 pi times 500 hertz. Good? Everyone understand why I have this 2 pi here? Yes, angular frequency versus frequency. Yeah. Okay, wave oscillation 2 would be the exactly same functional form. In fact, for the perfect kind of wobbling here, cancellation you see here, you want them to have exact same amplitude. So same amplitude times, I guess it could be sine, but I'm going to make it cosine to make it easier for myself. So cosine of omega 2t. And in the example you're looking at, omega 2 would be 2 pi times 505 hertz. Okay. I'm writing the numbers down here because for this beat to be very noticeable, it's actually important that these 2 frequencies are slightly different, but also only slightly different, that they're very close to each other. If it was 500 and 1,000 hertz, you would not hear the same thing that we were hearing just now. So, so we are going to try to look at the result of interference between these 2. What do you do when you say 2 waves or oscillations are interfering? Like, what's the mathematical procedure you use to get the result? What's the combined effect of F1 and F2? Asia? Yeah, just add them. Superposition principle. Remember that we give it a fancy name because it's the simplest mathematical operation there is. This is even simpler than an average. If you're averaging them, you now have to divide by 2. This is like what other mathematical operation between 2 objects are there that's simpler than addition? So yeah, we simply add them. Now, when I add these 2, this is the result you see. So I can factor out A, and this is what you see. A times cosine of omega 1t plus cosine of omega 2t. Now, which one of you, looking at this form of a trigonometric function, say, oh yeah, it makes sense that this should look like this? No, not really, right? So what this is describing is, it's describing a time varying, or it's describing an oscillation with amplitude that's varying as a function of time. Let me see if I can zoom in more. So the one way I can kind of describe this is I can say that there's a function that describes this higher frequency oscillation inside. That's kind of like 500 hertz oscillation. And then there's a much slower oscillation. That's the envelope. So one way I can describe this function is as this. A product of, let's say, cosine of omega fast t times the envelope. Cosine or sine, doesn't matter. Cosine of omega slow times t. Like, does it make sense to you that if I wrote down a function in this form, that does represent this? Yes? No? Right? This is the time-varying amplitude. This is the faster oscillation inside the time-varying amplitude. Okay? I'm looking for your reaction because the next step we are going to go through is mathematically more complicated. If this portion doesn't make sense, then we should stop here and spend as much time as we need until this makes sense. It makes no sense for me to go into something that's more mathematically abstract when this doesn't make sense. Yeah?
I just don't understand why it's multiplied.
Okay, so let me just try to describe the amplitude of a wave. Something that's varying as cosine, right? So let's say I have a cosine wave of a particular amplitude. In fact, I could be trying to describe this. If I'm trying to describe this, that would be cosine wave of a particular amplitude. No? Cosine wave of particular amplitude. Let's say it's a cosine of omega t times a. That a is my amplitude. Yeah? And if I'm looking at this wave, then that a is a constant. As I move across different time, the amplitude doesn't change. It's the same amplitude throughout everywhere, every when. So okay, this describes this, just a single periodic thing. The result of the interference is this. Look at what happens to this oscillation as I go through different time. Amplitude increases, then decreases, and increases again, then decreases. So this A, amplitude, instead of being a constant, it now has to be a function of time. And what I'm saying is, all right, I'm trying to describe this amplitude as a function of time. That looks like something that's cosine or sinusoidal. Like imagine following these peaks. So it's increasing like a sine of omega t, and then it's now decreasing, and then you have to kind of imagine following it through to the negative side, and then to the other side of the sine, and then keep going, and when you come back all the way here, this is now one full sine wave of this a of t. Yeah. Or to use the form that I was writing down, you would imagine a of t starting from this point right here. So this is cosine of 0. And then as time goes, this amplitude decreases. This amplitude decreases like cosine would, eventually crosses 0, and then goes into negative. Now, when the amplitude is negative, you still have this oscillation because this can also be negative. So the product can be positive. So it's down here, keeps going. This is the cosine of minus 1, that's I guess pi phase later. And then you keep going, and then this comes back. This is 3/4 of a cycle. And then all the way back here, that's now one full cycle of cosine of omega t. Okay. So that's describing how this amplitude is changing as a function of time. So we are using amplitude as a function of time is, well, some fixed amplitude times cosine of however slow that amplitude was changing. That's why I called it omega slow t. Does this make sense? Yes. Yeah, so that's the result we are trying to get to. And it's several steps from here to the result we are trying to get to. We want to get to a point where we want to rewrite this expression so that it looks like a product of two sinusoidal functions. Right? So, all right, and let me show you the steps that's needed to get to that, because the rest of the steps here, it's kind of unintuitive. I mean, if you can follow through the steps, then that's fine. But if you're not able to predict what I'm going to do, that's understandable, because what we are now going to do is somewhat poorly motivated. As in, it's not clear what the reason is why I do the things that I'm doing. The only thing that hopefully is clear is that what I'm doing is mathematically correct. I'm not making any mathematical mistakes. So let me start out with this. I'm going to rewrite omega and omega 2 in terms of something different. And that motivation I can actually explain. Do you remember how we worked out the standing wave interference? Like what mathematical tools we use to do this? Not double angle. Is that what you said? After what did you say?
Yeah, that's what
Yeah, we didn't use double angle formula, although it is related to double angle formula. Well, we used the trig identity, right? Yeah, we used the angle addition formulas. So the formulas we used were, cosine of alpha plus minus beta is cosine of alpha, cosine of beta, minus plus sine of alpha, sine of beta. And you can derive double angle formula from this. I would actually memorize this rather than the double angle formula, because you can't go the other way. Sine of alpha plus minus beta is equal to sine of alpha cosine of beta plus minus sine of beta cosine of alpha. Right? That's what we used. And after using it to separate this out, we saw some terms cancel out. And the term that remained was a product of like cosine of kx times cosine of omega t. Or it might have been sine. The point was it was a product of two trigonometric functions that describe the standing wave. So that's what the same thing is what I want to do here, except I'm stopped by the fact that this is a single term. It's not two terms that's adding. So the very first thing I'm going to do is I'm going to redefine two quantities so that I can express this as an addition. As an addition and subtraction. So these are the quantities that I'm going to define. This you just kind of have to know. I'm going to define an average angular frequency. Define the way you would expect an average to be. Omega 1 plus omega 2 over 2. That's average. And I'm going to define what I'm going to call delta omega, but in a slightly odd way. I'm going to define it as omega 1 minus, I'm going to define it as omega 2 minus omega 1 divided by 2. It's this dividing by 2 that's a little bit odd. But that'll make my future expressions simple. So having written these two, I can actually write omega 1 and omega 2 in terms of these two. Let me write down the result and see if it makes sense. Omega 1 is equal to omega average minus delta omega. Omega 2 is equal to omega average plus delta omega. convince yourself, so this is easier. Add these two, omega 1's cancel. Omega 2 is omega 2 over 2 plus omega 2 over 2, that's omega 2. Stephen, you had a question? Okay. When you're subtracting, it's the omega 2 that cancels, omega 1 adds. So you get this. This is not difficult algebra. You should be able to do this in your head. I mean, the why I'm defining this may not be clear, but you should be able to verify for yourself that this is true statement once these definitions are made. So this is something that I'm going to do that with no other explanation than this will help me rewrite this so that I'll have two terms. And those two terms will allow me to use this. And I'm hoping something will cancel out, and I'll get something that looks like a product of two trigonometric functions. So let's see if that works out. Let me, I guess, use this space here to write this out. So it's going to be the amplitude A. Let me do that in different color. Times. Let me write this. I guess I'll just write it out. Cosine of, I'm going to use this. So cosine of omega average t minus delta omega t plus cosine of omega 2. So omega average t plus delta omega t. Okay. I finally have two terms that involve where the argument to the trigonometric function involves difference and addition of two terms. That's now beginning to look similar to what we did for standing wave. So let's continue. I'm going to use my cosine angle addition formula to expand each of these terms. And let's see what happens. Write this out here. So amplitude A times cosine of, let me write that out, omega average t times cosine of delta omega t. It's minus, so it's plus. Plus sine omega average t times sine delta omega t. This is the first term here. So this first term is expanded out as this. I need to handle the second term still. The second term is plus cosine of, so it's sum, so do the same thing as before, cosine of omega average t times cosine of delta omega t. And then it's plus, so it's minus here. Minus sine of omega average t times sine of delta omega t. And when you have written this all out, this is the entirety of the second term. And if you have an eye for algebra, if not, develop it as soon as you can. These two terms cancel out. These two terms look exactly same as each other, except for a difference in sign, plus and minus. So they will cancel each other out. The remaining two terms, well, they look exactly same as each other with the same sign. So this is going to end up being equal to 2 times A cosine of omega average t times cosine of delta omega t. Good? Which of these two is the faster frequency? The average frequency or the delta omega? Delta omega is faster? Plug in the numbers, please. So that's why I gave you the numbers, so that you can actually try it out. So the average frequency, well, add these two together, divided by 2. So the average here should be equal to 2 pi times average of 505 and 500 and 505. That's 502.5 hertz. What's delta omega? Yeah, 2.5. 2 pi times 2.5 hertz. Which is the faster frequency? The average, yeah. The average is at more or less at the same frequency at these initial frequencies started out at. So we have a word for frequencies like this. This is called carrier frequency. It's the same word as your cell phone carrier, because those radio frequency or microwave frequency signals work on the same principle as this. There's a carrier frequency of, I don't know, 2 gigahertz or 3 gigahertz for your phones. And the way data is sent is by modulating that 3 gigahertz carrier frequency signal. And this delta omega is related to what we call bit frequency. So I need to, so delta omega is not the bit frequency itself, so I should write down the bit frequency somewhere. So bit frequency is defined as omega 2 minus omega 1. It's the difference between these two frequencies. So if you want to express it in terms of delta omega, it'll be equal to 2 times delta omega. It's sort of, this 2 here is there for the same reason that this 2 is there. Sort of, it makes your mathematical expressions look nice. But otherwise, yeah, this 2 is here, so this 2 it has to be there. Okay. All right, so that's the mathematical result, and this confirms what you already saw, that when you add these two waves, then the resulting form is this, which we said before that it looks like this looks like a product of two cosine functions, or product of two trigonometric functions, sinusoidal functions, and that's this result that comes out of this trigonometry algebra. Okay. I guess I want to end with one more demonstration of bit. When I was playing with this, I realized that none of this is actual physical illustration of bit, as in even when I do this, like even when I pretend that I'm playing two sounds at the same time, it's not really, because within the software, the sound card, mixes it, produces what was the mixed and rendered the track, and then plays that. So you might believe that, okay, all this works out mathematically, but what if this effect is not physical? Like if it doesn't happen really physically. So that's why my second laptop is here, so that I can actually generate sound from two independent sources, and you can hear that the beat actually happens. It doesn't happen as nicely as if they were on the same computer, but it does happen. So let me show you. So I can't really project this screen, but I can play the sound so that you are still convinced. So I kept the 500 hertz track there, right? So let me generate here a 505 hertz track. Okay, let me just play them separately so that you can hear the original sound. That's 500. This is 505. Doesn't sound all that different, right? My computer has a weaker speaker, so it's not as loud. But all right, let's try playing them both at the same time. Do you hear the wobbling? Yeah. So So that's the bit. That's what you hear when you hear two different frequencies that are different, but only so slightly. So, all right, so that's, I guess, all the time we have to spend on the bit.
So you've seen my standing waves lecture already. I have done this with the real functions, the sine and cosines. And standing wave, it's a really fascinating phenomena, and the one that's more ubiquitous than you might guess just at this early stage. Well, the whole phenomenon of a wave is more ubiquitous than you might guess at this early stage. And standing wave is kind of it's what you get whenever you have a resonance. You saw that in your standing waves lab. So the kind of the easiest, the simplest visualization of standing wave is with a pattern that you will see when you set up a wave on a string. So let's say you have one end of the string tied down at the wall or a post, and you have a string stretched out, and you shake it at the other end. But you shake it in such a small amount that you can consider this end as being fixed down compared to everything else that's oscillating. Then you have seen the lecture demos with standing waves of this form. As it shakes up and down, it kind of shows this shape. This is the standing wave of the form where the wavelength is double the length of the string, and as you shake it at higher frequency, you get shorter and shorter standing waves, ones that look like this. And over half a cycle, it goes into this shape, and then just one more that looks like this. So you've seen this in demos, both real and virtual. And then after having demonstrated standing waves, we've talked about what kind of how to get, or in some way to think about what other things the standing waves are made out of. With the help of superposition principle, we've given this description of standing wave. That the second standing wave up there, that can be thought of as a kind of combination of two waves, one that's propagating to the right and one that's propagating to the left. I'm not drawing it well. Imagine they're the same wavelength. And as those two counter-propagating waves, they overlap, they add, they go through superposition principle. You get certain points, like a point here where, I didn't draw it right. Certain points where they always destructively interfere, so they don't move up or down. And in order to get that description, we gave a description of these traveling waves. And when we were, and the description that we gave was, let's say, the wave that's traveling to the right as a function of position and time. It might be some amplitude times the sine of kx minus omega t. And the wave that's traveling to the left, that would have been given as some amplitude times sine of kx minus plus omega t for the wave that's traveling to the left. And you can figure out what this signs means by considering what happens when you consider greater time. As you consider greater time, do you have to increase or decrease x in order to stay on the same point of the wave, same phase of the wave? And it's this one that's traveling to the left, it's this one that's traveling to the right. And we've shown with the use of trig identities how by adding these two, you can get a function of the form that looks something like some amplitude times the time and the position dependence kind of separates out. So you might have something like a sine of kx times cosine of omega t. So you've seen that done in the real functions, and that's I do think it's instructive to go through it. So I would not recommend the people not to go through it. It does take some use of trig identities, and those identities you see being used are the ones that are quite important in many different physics calculations. The angle addition formula, like that's the one the trig identity that I tell you to memorize. Oddly not emphasized in. I don't think it's emphasized enough in your calculus and trigonometry classes.
So anyways, so now what I want to do for the remainder of this lecture is the second part here, standing waves with the complex exponentials. I want to show you that you can do the exact same calculation using complex exponentials, which you might have seen if you looked at the optional lectures for the simple harmonic oscillators. Really, the complex exponential is how we handle any oscillatory phenomena. So how we handle oscillatory phenomena in physics and engineering. You've seen with the simple harmonic oscillators how use of complex exponentials really simplifies the problem. It turns a calculus problem into an algebra problem. And in the context of derivation of standing wave forms, I guess what it does is it avoids the need for memorizing trig identities. So in order to do the calculation you saw me do for this, I had to memorize angle addition formula. Now, for this derivation that you will see for the next 15-20 minutes, you will see me using nothing but this one formula, which is Euler's equation that that should have been covered in trigonometry class. But I do think many math instructors might skip it. I have seen it in trig textbooks in like an optional section, ones that not everyone might cover. So what Euler's formula says is this. You can give a meaning to something like E, Euler's number, to the power of I times, let me call it X. So it's some imaginary number up there. You can give meaning to this imaginary exponent. And that meaning comes down to cosine of X plus I times sine of X. The way you would prove it is you prove it using Taylor polynomial. So if you wanted to prove it, you can prove using Taylor polynomials. So when you use complex exponentials to deal with oscillatory phenomena, this is what you do. You take the functions that you might have written in real trigonometric sinusoidal functions, and you write there the complex version of it. So I'm going to write it this way. Let me write that. The complex version of the right traveling wave is going to be, it will have the same amplitude times, and where I had a sine of kx minus omega t, it's going to be exponential of I times that argument that's within the sine. Now there's a bit there that I have to be careful with, so let me take that care now and fix it now before it gets any further. So when I was dealing with the sines and cosines, I wasn't all that careful about the meaning of this k wave number and omega angular frequency. So let me write down k wave number, omega angular frequency. And by being careful, this is what I mean. It's the question of, are they vector quantities or are they scalar quantities? When you're looking at these expressions, it might not be obvious to you which one's vector, which one's scalar, and they're the same. And so the wave number is actually a vector quantity. It's a quantity that corresponds to the direction of the wave of propagation. So in a three-dimensional version, this expression would be written something like k dot product with delta r plus omega t. So this wave number quantity is a vector quantity that has a direction. Direction actually matters. And omega angular frequency, this is the one that's a scalar. The direction doesn't matter. The only thing that matters is the size, magnitude. So once you are aware of that, then you might notice that how we assign the minus sign is actually a little sloppy, because our change of sign, that happened with omega, not k. And if k is the quantity that carries the direction, then that's the one that whose sign should change when you change the direction. So let me write it out this way. So I think I still needed opposite signs between these two. So the way I'm going to write it is, let me just swap the orders so that I can take a care with how I write kx. It's going to be minus omega t plus kx. and this plus sign here will mean that this wave is traveling to the right. And let me write my other wave. That's gonna be the complex wave traveling to the left. Everything else the same. And it has the amplitude. And for future convenience, I'm going to add a little term here, which is what I'm gonna call phase factor. So in terms of the complex numbers, the magnitude doesn't change, but what this lets me do is it lets me shift the timing of the other wave coming in. Depending on how it's timed, you might get one form or another form. So this is a degree of freedom I'm giving myself so that I can have different ways of adding these two functions together. If anything else, I can set this to 0. In fact, we'll do that as a first example. So that times, I have the same expression, exponential of I times, and the first part will remain the same. It'll be minus omega t. And what I'll now change is have this as minus kx to indicate that it's traveling to the left. And you can see with the trig functions how whether I wrote both plus kx plus omega t or minus kx minus omega t wouldn't have made a difference. That just changes the sign of the previous coefficient if it's sine, because it's an odd function, or if it's cosine, it actually changes nothing at all because it's an even function. So as we are working with the complex exponentials, I am being careful about this particular meaning of wave number and making sure I have this written in a mathematically correct form, because otherwise I'll get into mathematical trouble. So with these two functions, so what I'm going to do is I'm going to apply superposition principle and see what I get. See if I can do something similar to what was done before using real functions. Now, it won't look exactly the same because I am using complex functions, so some of those complex factors will remain. What I'm hoping to do is I can keep all that complex stuff with the oscillatory portion of the of my wave expression, and kind of the things that relate to the spatial representation. Somehow I can write a real function out of that. So it's okay. Let's get started. I'm gonna scroll down and let me just copy this over so that I can refer to it later when and if I need it. So we'll follow the same steps that we've gone through when we did the standing waves derivation with the real functions, which is we are just gonna add these two counter-propagating waves together and see what happens. And as we do that, so I do have to make a choice about this phase factor that I introduced for the purpose of giving me some degree of freedom. So we'll work with phi is equal to 0 first. Let's see what we would have gotten if I didn't introduce this, and then just go from there. So we are working with a case where phi is equal to 0. That's where these two waves, have no well, I don't know. The relative phase is kind of relative to how you set the references. So I'll just say this is phi is equal to 0. And later on we'll look at, phi is equal to pi or phi is equal to pi over 2. We'll see how they combine differently. So let me just write that. So my function g will simply be sum of phi plus, f plus f minus. That's how my g as my complex combined overlapped interfered function will be. So I'll just write down g as that. So let me just write out the whole expression. A times exponential of I minus omega t plus kx plus with a phi equal to 0, e to the I 0 is just 1. So it'll be a times exponential of I minus omega t minus kx. And I see some things I can factor out. So I can factor out a, it's common in both terms. And with these two exponentials, I can imagine doing a little bit of exponential algebra to rewrite this as e to the I minus I omega t times e to the I kx and e to the minus I omega t times e to the minus I kx. So I can factor out these two common terms. So factoring out those two things, I get a times e to the minus I omega t. I like what I see because I'm separating out the time dependence the way we did it when we were working with the real functions. And the remaining terms look like it's this and that term. So it'll be e to the I kx plus e to the minus I kx. So looking at it, you might think, okay, I think I have some sense of what this means. Oscillation amplitude and oscillation frequency. Kind of like when we were looking at simple harmonic oscillator. Now you might be staring at this and not being sure what is this. So one of the things that we can do that will actually help us make sense of this expression is to apply Euler's formula. That's why I copied it down here, so that I can just using this expand out what each of these terms are. So let me do that. Let me do it in place just to save a little bit of space here. So let me just move this out. And where I had the e to the I kx, I can rewrite as cosine of kx plus I sine of kx. So let me write that up. Cosine of kx plus I sine of kx. All right. Plus, and let's write out what the other term was, where we had e to the minus I kx. So what this really is it's e to the I minus kx. So this minus kx goes into argument of the two functions. So cosine of minus kx plus I sine of minus kx. Okay, let me clean this up a little. So if you're looking at this and thinking that you just made things more complicated, this is why I encourage you to practice simplifications. You can actually simplify this quite a bit. So you use the properties of cosine and sine functions. Cosine is an even function and sine is an odd function. And what that means is when you have a minus sign in the argument, you can do certain things with it. With the even function, this minus sign just can be ignored. It's like, even like a parabola is an even function. Whether a minus side, the plus side, the value you get is the same. So you just turn the minus into plus, you haven't changed a thing. With the odd function, that's just a line, function of a line, that's an odd function. Where, so what it means is, if you go from plus to minus, whatever value you had, you get negative of that value. So where you have minus, you can pull the minus sign out of that the function argument. So minus in front, plus here. Now, once you've done that, you should be able to see the simplification. The cosine functions and the sine functions, because they are the same term with the opposite signs, they cancel. So I can cancel out the sine of kx, and I get just cosine of kx. So let me just turn this into 2 and get rid of that. Let me just clean this all up. So you get a cleaned up version of 2 times a e to the minus I omega t times cosine of kx. So you have this function separated out. You got some time dependent oscillatory thing that'll have all the complex things in it, and you get this real function that basically gives you the shape of your the standing wave function. Now, the functions that we looked at up there, they might not have looked like cosine of kx, any of them, if I set my x equals 0 here. But imagine if your x was set to equal to 0 somewhere in the middle. Like this is where x was equal to 0. Then this waveform here, this is cosine of kx. It's a matter of whether you have cosine or sine. It depends on kind of setting your origin correctly. Or I think if we really want a sine function shape, I think we can get it by messing with this phase factor. So let's try a few other values of phase factor and see if we can get this function to go as a sine of kx instead of cosine of kx. So so one of the phase factors I want you to try, let me do it this way. I'm going to move this down and just use this space again so that I can more easily refer to these functions. So let me move this down. So, so let's do this calculation again, this time with phi value of not zero, but so if you think of phi as an angle, you know, from 0 to one that can go all the way to 2 pi, which is 0 again. The one that's most opposite is pi. So let's see what we get with the phi is equal to pi. So phi equal to pi. And we'll add these two functions together again. My g is a times, let me this time just write this separated. So it'll be e to the minus I omega t times e to the I kx. And then plus, and this will be a times e to the I pi. And I can simplify this a little bit. I'll do that in a little bit. That times e to the minus I omega t times e to the minus I kx. So you simplify this the way we were simplifying before using Euler's formula. That's why I had a copy down here. So imagine putting in, so for e to the I pi, imagine putting it into this function here. So cosine of pi plus I sine of pi. Sine of pi is 0. Cosine of pi is minus 1. So this just gives you a factor of minus 1. So when we factor out the common terms again that we are factoring out before, what that expression now becomes is a times e to the minus I omega t. And the terms that remain are e to the I kx. And instead of plus, it will be minus e to the minus I kx. So let's, parenthesis too small. So let's write it out here. I think if I save space, I can kind of fit it in the remaining space. So we'll say this is equal to the terms that we've factored out. And I'll just write down each of these terms using Euler's formula. So I have cosine of kx plus I sine of kx. And I'm going to remember this minus sign and put it each time as I write it down. It'll be minus cosine of minus kx, and then minus I times sine of minus kx. Let me simplify these minus signs again using the property of cosine and sine, even and odd functions. So this minus sign just goes away, doesn't do anything. This minus sign gets pulled out and turns this minus into plus. It becomes plus itself. So, okay, so I think I have different functions canceling out this time. So cosine kx, still the same term, but this time with a minus sign. So these two will just cancel out, and I can combine these two into 2I sine of kx. So when you write that down, what you get is 2a e to the minus I omega t times, now there's an imaginary number. So I times sine of kx. Now there's a way to kind of rewrite this, which is kind of work your way back through the Euler's formula. Or you can imagine doing this. I happen to know the exactly right number. So let me just do that with the exactly right number. If you are putting in e to the I pi over 2 into Euler's formula, then what you will get is cosine of pi over 2, which is 0, plus I times sine of pi over 2, which is 1. This is 0, this is 1. So e to the I pi over 2 is equal to I. Or I can flip that around and say this I can rewrite it in terms of as the complex exponential. E to the I pi over 2. And I can, oh, look at that. I can do a little bit of exponential algebra to combine these two things. Say 2a times e to the minus I times omega t minus pi over 2. So that complex factor in front, it's a phase factor. It amounts to like an offset in the time where you start the time, times sine of kx. So if you wanted to get your get your wave function, get your standing wave shape to have look like something based on sine of kx. That's great. You can do that. Just start the two counter propagating waves. Start them in such a way that one of them is offset a little bit in time, by this phase vector of pi. Then as they overlap, they in the coordinate system you're using, they will look like a sine of kx. So sine of kx can be used to describe basically all the shapes I drew, with the x equals 0 here. Like everything here can be described as some for some value of k, sine of kx. So yeah, those are the two different phase vector values, which can give you these two different shapes of standing waves. These two phase vectors, either the phase difference of 0 down here, phase difference of 0, which leads to the wave form looking like a cosine of kx with a particular origin set, or either you are looking for standing waves of a different shape, or you are looking for a kind of where your origin has been shifted over. One way you can do that is by looking at different phase vector. Then you can get with a phase vector of pi, you get standing waves that go as a sine of kx. So this is the demonstration of use of complex exponentials to do the same derivation that you have seen with the trig functions, except here I didn't have to memorize any trig identities. The only thing I had to know was Euler's formula, which is a way to kind of convert back and forth between complex exponential form and its representation in terms of sine and cosine functions. And Doppler shift comes up also in other context of other traveling waves, like visible light is a traveling wave, electromagnetic wave, and we talk about Doppler shift of light as well. In that context, we talk about red shift and blue shift. That's the astronomy context, and so that's in the very big picture terms, that's what Doppler shift is referring to. Shift in frequency or wavelength of a traveling wave that depends on the motion of the source or observer. As I was preparing for this session, I found a simulation that can be used to illustrate where Doppler shift comes from and what are the factors that affect it. So yeah, it's this one. So let me use this simulation to visualize a Doppler effect. So it's a simple simulation. It by default, this sets up a situation with the source and the observer at rest. And it has some frequency of emitted sound waves and some frequency at which it's observed. So let me just play, then you will see what the simulation visualizes. It's visualizing this. Those pulsing, outgoing, circular waves, you can imagine them as wave front of a sound wave. And so imagine this is a very slow motion version of it. So this is well, I guess there are different ways to imagine it, but so if spacing between these somehow correspond to 100 hertz, then as the sound waves reach the observer, then the spacing remains the same, so the observer will hear it at 100 hertz. Now, let's change the parameters of simulation a little bit. So we could make it so that the sound source is moving. When the sound source is moving, watch what happens. So before that, let me just play it for a while again so that you get a sense of the kind of the rhythm of these waves being emitted. So it's the rhythm at which wave is being emitted. And I'm going to have the sound wave source move. Let's have it move towards the observer, positive velocity, at some fraction. So it's in units of speed of sound. So I think if I make the source move at something like so this is 50% of speed of sound, so it's actually pretty fast. In the real world terms, sound waves move at about 340 meters per second. So here the source is moving at something like 170 meters per second. In terms of miles per hour, that's like 300 miles per hour. So we are talking about something like a small airplane, something that's moving very fast. So if you imagine this is the source that started out from somewhere here, so at this position is where it emitted this sound wave that's represented by this wavefront. And you can see that by the time this second wave was emitted, the source moved here. And as it's emitting this third wavefront, it's moved here. So let me play for a bit. So you can see the pattern build up here. So on the right side of the source, as the source emits the wavefront each time, it's getting closer to the previous wavefront it's emitted. So there's a kind of bunching up of the wavefront on the right side of the source. So when the stationary observer is listening to the sound, then the sound is at a higher frequency. I guess the simulation is saying it's at 200 hertz. So that's what the observer hears. Now, if the observer is on the other side, then as you can see from this wider spacing, you can see that this observed frequency will shift. Let me just continue running this step by step. And once the source passes the observer, then now the frequency shifts. Instead of hearing a higher frequency, the observer hears the lower frequency. And actually, that's the video that's linked from the lecture page. Okay, unmute. And let me just play it through 30 seconds. That ambulance is probably moving at something like 10, 20 miles per hour, maybe 30. 30 is probably like 20 miles per hour. So it's that's moving a lot slower than how I was simulating the simulation, because that's only like 10, 20 meters per second. But our ears are sensitive enough that you can hear that difference, shifting from, I don't know, 800 hertz to 750 hertz. And the difference here is difference in the simulation is a lot more dramatic. And one advantage of simulation is that it can also demonstrate some things that that's not as maybe a little bit harder to well, that I can find the videos of. So here you are seeing Doppler effect in the scenario where the source is moving. You can visualize it like how the simulation showed, and it's great. If that, I hope that all makes sense. Let's look at a couple more slightly less intuitive setup. So we are going to go back to making the source stationary, because we worked with a moving source. So let's just have the source stationary, and let's have the observer move. So have the observer move towards the source, so negative velocity at half the speed of sound. So this time it's the observer who's moving at something like 300 miles per hour. So let me just play it for a bit at a normal speed, and after a bit I'll just step through. So this is how it looks. Now, as you look at this, you might think, so this spacing hasn't changed. So why is it that observer is hearing a different frequency? You have to think through the time between the wavefront for the observer. So let's say observer is crossing this wavefront here, and now if the observer just stayed at this point, the amount of time it takes for the next wavefront to reach this point will be same as what you would expect for 100 hertz. But the observer doesn't stay stationary. as the other wavefront is coming towards the observer is moving towards that wavefront. So they meet together somewhere here at an earlier time than when the at an earlier time when this wavefront would have met observer if the observer remained stationary. So a shorter period, shorter time between the wavefronts means higher frequency, and that's what you see here. Emitted frequency is 100 hertz, observed frequency is 150 hertz. Let me just play through, and once the observer gets to the other side, then the observed frequency is lower. You can kind of see why. So let's see here. Oh, that wavefront already crossed the observer. So, okay, here, this wavefront is crossing the observer. And if the observer stayed here, then this next wavefront will hit the observer around the time when you expect a 100 hertz wave to hit them. But because the observer is moving away, by the time the next wave is able to catch up with the observer, the observer has moved this distance. So the observed frequency is less. Now, if you're paying careful attention to these numbers, you might have noticed that these numbers changed. As in, when you had the scenario where so let me bring it back to the previous scenario, where the observer was stationary and the source was moving at half the speed of sound. The higher frequency was a double, and the lower frequency wasn't quite half, but I don't know, 6, 7. So I guess that's 2/3. That's what you saw in the case when the observer the source was moving. Now let's change it back to where source is stationary and observer is moving towards the source. When the high frequency is not double, it's I guess 3/2. And the lower frequency is not 2/3, it's half. Now, I haven't tried it in this simulation before, so I don't know quite what it'll give me. So what I hope those who are curious will try is, so what happens if both the source and the observer are moving? So if they are moving towards each other, then I think you can imagine the Doppler effect will be larger than what it was when one of them was moving. But what if they are both moving, but in the same direction? Let's give that a try. So let me have the source moving to the right at half the speed of sound. And let me move the observer also to the right at half the speed of sound. So when you have that, okay, yeah, the simulation is wrong. I think. Because is it wrong? It might not be wrong. Thought there should be still a bit of a shift. But I think one thing that's still okay. This part I field tested before. I'm not quite sure. This could be right, but I think one thing that's even so that's good to note is that the exact amount of shift, it depends on whether it's a source moving or it's observer moving. So because this is something that someone who's physically astute might intuitively think. Someone might intuitively think that these two physical pictures are the same, where the source is moving towards the observer at some speed. You might think that's the same situation where the observer is moving towards the source at the same speed. But you can clearly see in this simulation that they are not the same. You observe one frequency in one scenario, and in the other scenario where one might intuitively think is analogous or similar to the other setup, you observe a different frequency. And this is something that's more useful and salient to note when we do in physics 4C, when you do special relativity, about how there's no special inertial reference frame. Here, what it is demonstrating at a minimum is that when you are dealing with a sound wave, there is a special frame where things are at rest. And it does make a difference whether it's the source moving relative to that reference frame or the observer moving relative to that reference frame. And that inertial, the reference frame where things are at rest, that's the reference frame of air. In the reference frame where air is at rest, that's the frame relative to which you measure all your velocity. So these two physical pictures, one where the source was moving versus one where the observer was moving, those are two distinct pictures. And all the illustrations in this simulation is done in the reference frame where the air is still. That's why it does make a difference whether the source is at rest or relative to the air or not. So so your textbook has a set of formulas that are derived, and let me see if my own intuition was off, because for some reason I thought when they were both moving in the same direction, then there should still be some shift. But it's possible that I got that wrong. So let's take a look at your textbook. It's in your section 17.7, the Doppler effect. I encourage you to read through that derivation. For our purposes, I'm just going to copy those formulas and use it. So it derives two different formulas. And it's important to note what conditions apply for each formula. And there's a indication within the derived formula for that. So it says when a source is moving and observer is stationary, and the indicator there is that they are telling you the velocity of the source. The S stands for source. So let me just write that out. The observed frequency is equal to the source frequency times the speed of the sound divided by speed of the sound. And this minus plus sign relates to whether the source is moving towards the observer or away from observer. Minus plus. Top sign is for source approaching the observer, so minus when source is moving towards the observer, and bottom sign is for source away from the observer. So this is one formula for Doppler shift. And because of that asymmetry I was describing, there's a second formula for when the observer is moving and source is stationary. And that they go through this consideration again. I encourage you to follow this derivation on your own. And this is the formula. So this is the scenario where the observer is moving. Then observed frequency is the source frequency times, and you see that the terms that are being modified is different. So it's the factors on the numerator that are getting changed for some reason. Speed of the sound plus minus speed of the observer divided by speed of sound. And let's see, look at the sign here. Top sign plus is for observer approaching the source. That makes sense. When the numerator is greater, the observed frequency is greater. So with the Doppler shift, you have to watch out for that. You have to first note, is it the source moving or the observer moving? And depending on which of the two is happening, you have to use appropriate formula. So if you are combining this into one equation, then that would be what they have here. And this combined into one expression is this. That all looks fine. V plus minus V observer divided by V minus plus V source. Now, so I guess according to this formula, then yeah, it must have been my intuition that was off. Because if you go back to here and imagine recreating the scenario, this is the scenario that confused me. Then you have this situation where the speed of the source and the observer are the same. And so VO and VS have the same magnitude. The source is moving towards the observer, so it's a minus sign for the denominator. And the observer is moving away from the source, so it's also minus sign for the numerator. So these factors cancel out, and source and observer frequencies are the same. Yeah, so I guess it's So let me just leave that there. So if both source and the observer are moving together, then yeah, the observed observed frequency is the same as the source frequency. Okay, so I think that's enough for the one homework question you have. Let me just end with a demonstration of a shock wave front. So this is something special that happens when the speed of the source, not the observer, exceeds a particular value. So I mean, I guess something weird could also happen if the observer velocity exceeds this value. But let's say for simplicity's sake, we're dealing with a stationary observer. That's usually the case for this scenario. And let me put the source way back so that there's enough of a distance. So this is the special scenario, and you can kind of watch this here. I'm going to set source velocity at higher and higher velocity approaching some value. So this is in units of speed of sound. Let me make it faster and faster up to a value. So 10% of speed of sound, 20, 30, 40, 50, 60, 70, 80. Okay, I can go up to 90. 90. So at 90% of speed of sound, you see something happening here. The wavefronts at front, they start bunching up really close together, and the observed frequency is actually getting pretty high. And if you think back to the Doppler shift formula for moving source, as this velocity, the speed of the source starts to approach the speed of sound, something's happening with the denominator there. So you might wonder what happens if these two numbers are the same, so that you are dividing by 0. Well, this happens. And I guess if the observer is directly in front of the source, then it's going to get hit. So let's imagine an observer who's slightly away. Then you can see that the kind of sound wave an observer who's here would hear is a little bit different from the kind of the sound waves that someone who's here would hear. Because right now we do this 60% of speed of sound. It's just regular sound, nothing unusual. But when it's at equal to the speed of sound, then this bunched up wave front, they extend down to here. So what you can imagine is an observer who's here is going to feel the effect of all those wave fronts constructively interfering at the same time. And that's what's referred to as a sonic boom or the shock wave, because when all those wave fronts are hitting you at the same time, it's quite loud. And the one or Mach 1 is a bit of a special speed. I think there's a lot of instability there, as you can imagine, division by 0. So let me actually move it off to the other side. Make the source move at 1.5 times the speed of sound. That gives a more cleaner illustration of the shock wave. So I gotta know when to pause it. Let me pause it at the right time. So these wavefronts look qualitatively different from previous wavefronts. So for one, the source will reach the observer before the observer even knows that source is coming. I mean, if they see it, then they will see. But the source observer will only hear the source after it's passed. And imagine someone who's down here. So this is the representation of the shock wave front. And this is the front where all these different wave fronts have constructively interfered. So as this passes through whoever's down here, they will hear a very loud sound in a very short duration of time. That's the sonic boom. And that's why supersonic airplanes are banned from airports near the population centers, because they're quite loud and there's not a lot of things you can do to stop them from being loud. And that's the illustration of shock wave. And that's what happens when the source moves faster than the speed of wave. This happens with the sound wave, quite obviously, and you can also hear it from time to time when you're in the right place at the right time. And this can also happen with the light waves. So with the light waves, you need a very specific setup because light in vacuum is the fastest thing, so nothing will move faster than that. But light in a transparent medium it is not necessarily traveling at the same speed as vacuum. So in medium like water or glass, source of light wave, like electron, can move faster than speed of light in that medium, and you can get a light shock wave that's similar to this. So I think that covers all the stuff about sound waves that I've avoided lecturing on in the past.